In this video, we're going to look at quadratic functions. In order to do that, I'm going to start by defining two forms of the quadratic function, the standard form and the general form. If we look at the standard form, f of x is equal to a, in parentheses, x minus h squared, plus k. The standard form tells us a lot. So first recall that a quadratic function is a parabola. It is that U-shaped figure that either opens up or down. The first thing that we can get very directly out of the standard form of the equation is whether it does open up or down. The a term tells us this. So if a is greater than 0, positive, it's going to open up. If a is less than 0, it's going to open down. The other thing the standard form gives us very directly, very easily, is the vertex of the function, the vertex of the parabola. So remember, the vertex is that point where the function changes from increasing to decreasing, or decreasing to increasing, as I've just drawn. So one of these 2 points right here, wherever it turns, that is the vertex. So in order to find the vertex, we only have to be able to read. The vertex is the point hk. We take the h out of the what's inside the parentheses and the k from what's outside the parentheses. Notice the h switches signs, the k does not. And that ties back into what we know about transformations. We know what this thing looks like in terms of transformations, and we know pluses and minuses are always shifts. Whatever's inside the parent function is a horizontal transformation, and it moves the opposite direction. So if we see a minus h on the x, that would be moving to the right by h units. The plus k on the outside, that would be a vertical shift, and they behave normally, so that would move it up. We look at the general form of a quadratic function, f of x is equal to ax squared plus bx plus c. The a's work exactly the same. If a is positive, the function opens up. If a is negative, the function opens down. What's a little bit different is the vertex. It takes a little bit more work to find the vertex. The vertex is going to be the point negative b over 2a. That gives us the x value of the point. And notice that looks pretty similar to the quadratic formula, not just by pure chance. Quadratic formula that gives us the x-intercepts, or the zeros of the function. Negative b over 2a without the plus or minus square root portion. And then to get the y value, how we always get a y value, we plug in the x into the original equation, and that'll give us the y value. So the vertex negative b over 2a, comma f of negative b over 2a. I'm going to do a couple examples of each of these. One for each of these. So if we look at the function f of x is equal to 2 in parentheses x plus 1 squared minus 3. First thing we need to recognize is what form this thing's in and what type of equation it is for starters. So I do recognize this is a quadratic equation because it has a squared on the x. And I recognize its standard form because I have that singular x term, just that one x term that is being squared. We don't have multiple x terms in this equation. So this makes it the easier type of quadratic function where I can recognize that, hey, my a is 2, that's greater than 0. Tells me right away my parabola opens up. And it also gives me my vertex right away. I can just look at the equation, see that my vertex, what's attached to the x there, the plus 1, has to switch, so that's going to be a negative 1. And then the y is whatever's on the outside, the negative 3. So already I have a pretty good idea of what this function is going to look like in terms of its graph. I know I have the point negative 1, negative 3 for its vertex, and it's opening up. But I'd really like a little bit more information to get a little bit more of a precise graph. So one thing we can always find pretty easily is a y-intercept. Let's go and do that. To get a y-intercept, we plug 0 in for x. 2 times 0 plus 1 squared minus a 3. So we'll have 2 times 1 squared, which is just 2. 2 minus 3 gives us a negative 1. So now I can go and put that point on my graph as well. Have a better idea of how this thing's looking already. I know that it's looking pretty steep as opposed to a more moderate slope. But let's go ahead and find some x-intercepts as well. They're pretty easy to find. We know how to find those, and that'll get us a couple other points for our graph. So if we think about the x-intercepts, we need to plug 0 in for y. 0 equals 2 in parentheses x plus 1 squared minus a 3. Now to solve this, a lot of times we would think we'd have to use a quadratic formula, but we don't in all circumstances. Sometimes we can factor it, and sometimes we would use completing the square, or if the square's already been completed, as is this case, we can just go ahead and kind of work it out. We can solve for x. Because we only have that singular x term, I'm going to work to solve for x. So the first thing I'm going to do is add the 3 to the other side. I'm going to try and isolate the x term. I've done that here. Now that I've isolated x term, I'm going to try and isolate the factor with the x in it, so I'm going to divide by the 2, so I'm going to get 3/2 is equal to x plus 1 squared. Now I need to get rid of that squared, so I'm going to take the square root of both sides, remembering to put my plus or minus in front of it, so I'm going to have plus or minus root 3 over 2 is equal to x plus 1. And finally, subtracting the 1, negative 1 plus or minus square root of 3/2 is going to be equal to my x. So if we want to approximate those values, because they're hard to plug in, put onto a graph, they're not exact values, break out your calculator, and let's see what we get. So when I plug these into my calculator, I got approximately 0.22 and negative 2.22. And that's what we see here. If we were to carry out our graph, that one's crossing approximately 0.22, and this one would be negative 2.22. So when those are exact values, it makes it a little bit easier to graph on our grid here. We get the right idea, we get the right picture. Let's take a look at the other form of quadratic. So here we have f of x is equal to x squared minus 2x minus 3. I recognize that it's in general form because I have multiple x terms. I have the x squared and the x term. So here it's going to require a little bit more work. First thing that doesn't require any work is realizing that, hey, that a value, what's attached to the x squared, is just 1. We don't see anything in front of it. It's understood 1, which is greater than 0, so we know it opens up. Second thing I would be able to get fairly quickly is the vertex. It's going to require a little bit more work than standard form. So to get the x position of the vertex, I'm going to take my negative b, which is a negative 2, so I'm going to have a negative negative 2, over 2 times my a, or 2 times the 1. Negative negative 2 over 2 is just going to give me 1. So I know the x position of my vertex is 1. To get the y position, I'm going to take that 1, I'm going to plug it back in. 1 squared minus 2 times 1 minus 3. So I have 1 minus 2, which is negative 1, minus the 3, negative 4. And so now I know my vertex is the point 1, negative 4. So if we start trying to plot these values, 1, negative 4, and once again I know it opens up, but it's again that question of does it kind of open very moderately or does it really open up very quickly? We don't know until we get a couple more points, so that's what I'm going to do next. Let's go ahead and find the y-intercept. Y-intercept is very easy when it's in general form. That's one thing that probably becomes a little bit easier. I can get the y-intercept by plugging zeros in for my x's, so I'll have 0 squared minus 2 times 0 minus 3, or just a constant value, negative 3. Negative 3 is my y-intercept, so I can put that onto my graph. Have a better idea. It seems to be tracking a little bit more steeply than the first set of dots, but a little bit steep, not quite as steeply as the second set of dots. Getting an idea of how it's opening. But let's go and get some x-intercepts as well. Now this time, because it's not in standard form, I'm going to have to use one of my other methods. So I can either factor, I can complete the square, or I could use a quadratic formula. If you're comfortable with factoring, if a polynomial can be factored, factoring is always the fastest way to go. So I'm going to look for that first. And I see the factors of 3 minus 3 plus 1 does in fact give me the negative 2. If you're not incredibly strong with factoring, if you can't find the factors right away, go ahead and solve it using the quadratic formula, because that's going to be the fastest option. If something doesn't factor, then there's no sense wasting all day trying to factor it. Just jump to your quadratic formula. But in this case, it's pretty easy. I say I get the x-intercept of negative 1 and of 3. And so I can connect my dots now. I have a nice picture of my parabola. A couple other terms that we haven't talked about. The axis of symmetry. The axis of symmetry is a line that we could reflect our parabola about, where it would be symmetric. So in this case, I'll put it in red on my initial function. Let me even switch to green so we see a different color. Or to draw a line right through my vertex. That would be my axis of symmetry. And notice that axis of symmetry has to pass through the vertex every single time, because the vertex is where it changes from increasing to decreasing. Because these quadratic functions always open up or down, the axis of symmetry is always going to be a vertical line, which a vertical line has the form x is equal to, and in this case, it would be x is equal to 1. So the axis of symmetry is just a line that our parabola is symmetric about. It runs through the vertex, and it is a vertical line, so we have to have that vertical line formatting x is equal to. One final thing to note, if we have a parabola or a function given in one form or the other, so let's take a function given in standard form, f of x is equal to x plus 1 squared minus 2. If I wanted to, I can always convert between the two forms. So if I start in standard form, by simply squaring this squared out, by foiling that out and then subtracting the 2, I will have it into general form. And then we'll see how to go backwards in just a sec. So let's start by squaring x plus 1. X plus 1 times x plus 1 is x squared plus 2x plus 1. Then we'll subtract our 2. We get x squared plus 2x minus 1. So these two polynomials are the same. These two functions are the same. We have the function in standard form and in general form. Notice here the vertex that we see would be negative 1, 2. Our general form takes a little bit more work. We'd take negative 2 over 2 times my a, which is just 1. I get negative 1, same as above. And then to get the y, I'd plug negative 1 in, negative 1 squared, plus 2 times negative 1, minus 1. 1 minus 2 is a negative 1, and then minus 1 is a negative 2, and what that shows me too is I drop my negative above. Please note that the standard form up here, the vertex was negative 1, negative 2. And then we get the exact same thing below, and I better, not a bad way to double check myself as I just showed, can pick up a dropped negative very easily. Let's say this time I want to start with the general form equation, x squared plus 2x minus 1, and I want to go to the standard form. Well, standard form is just a perfect square with that plus or minus k behind it and potentially a coefficient. So what I need to do is I need to create a value. I need to complete the square on this so that I get a perfect square. I'm going to have x squared plus 2x, that has to stay. I'm going to create a value right in here. I'm going to move that 1 to the back because as it was, x squared plus 2x minus 1 was not a perfect square. To create my perfect square, I'm going to think about, well, what is half of this x term? Half of the x term is 1, then I'm going to square that. Now if I just go adding values in that green blank, I have to keep the equation in balance, so I'm going to have to subtract it right back off again. I just, inside the parentheses, added a 1 squared, which is 1, so I'm going to subtract it at the back of the equation, and that keeps my equation in balance. By choosing half of that center value, the 2x, and squaring it, I've created a perfect square. So I now know I have the perfect square, x plus 1 squared, and then minus 1 in the back is a minus 2. That is how we would complete the square in our polynomial. Notice that we've gone right back to where we started at the very beginning before we went into general form. Completing the square, we're looking for that perfect square on the x, and then we have the plus or minus constant out back. That's what we got. Thank you.